We're in, so it's from section 11.3, using normal distributions. So reminding you from what we did on Friday, we had this group of racers in the charity race, the 5K race, and we took a sample of 40 women from the race and their finish times in the 5K race, and we made a relative frequency histogram. And so that looked like, so we entered our data into the list, into L1, figured out the mean, standard deviation, and then we entered our intervals in L2 and the frequencies in L3, and we went to stat plot, and we used those two lists, L2 and L3, and then we went to graph. And of course we made the window settings, what we needed them to be, and we graphed it. And so what this tells us then, this relative frequency histogram, if we hit trace, as we scroll through, for example, where I am here, it tells us that 27.5% of the runners finished the race between 22 and 23 minutes. And then I could scroll to the right, and I could see that 45% of the runners in the race finished between 23 and 24. So can you tell me kind of what shape this has, this histogram? Yeah? One? It's symmetric, right? And how many peaks are there? There's one peak, kind of symmetric. So it sort of looks like this bell-shaped curve, right? So then what we did is we drew over the top of it, because if the only question we wanted to ask is how many racers ran between 23 and 24 minutes, we would be done. But let's say it's a little more complicated. Like what about between, what we did is between like finish times between 22.5 and 24.5. How are we going to figure that out from these bars? It doesn't really fit in, right? So we drew this curve over the top like this, using this command, and so drawing it again, so we can approximate with a curve instead of using the bars. And then if we want to find whichever interval we want, the area under the curve, we just did, we used this command normal CDF, and we entered, like for example, between 22.5 and 24.5. How many racers, what percent of racers finished between those two times? And you have to give it the mean and standard deviation. Mean and standard deviation that we calculated earlier. And then we can see that 67% of the racers finished between those two times. So this is kind of the idea that we're now putting into notes to solidify. So that curve that I just drew is called a normal curve. So here we go. So a normal distribution. A normal distribution can be modeled. It's approximate. Can be modeled by a bell-shaped curve. A bell-shaped curve called a normal curve. Normal curve. There's your vocab word for you. And now the interesting thing that happens with this data, the way it's distributed in a normal curve, is that, so kind of just try to draw a nice symmetric bell curve on your paper. What will happen if this is the mean right in the center, and we'll put X bar for that, for the mean, then approximately 68% of your values will be within the first standard deviation of the mean. So if you go to about here and here, and we'll put this like 1 standard deviation, and we'll do -1 standard deviation. then 68% of your values are between there and there. So 68% are within one standard deviation of the mean. 95% will be within 2 standard deviations. So just draw, it's about a quarter of the way down would be 2 standard deviations, -2 to the left. Within 2 standard deviations is 95% of your values, and almost all of them are will be within 3 standard deviations if your data is normally distributed. So put that there, and 99.7% of your data or values will be within 3 standard deviations of the mean. That's supposed to go all the way across within 3 standard deviations. So we could actually put if we break this down and use a little bit of subtraction, we can put the percentages in each of these areas. So what do you guys think would go here? What percent is in this right here? Exactly. Very good. Because it's symmetric. So 34% is there, 34% is there. We'll use this in a minute for doing some problems. What do you think is in these spaces? What percent of the values would be under there? Well, if 95%, if it's all symmetric, right, and 95% is here, you would just do, can you tell me how I would get the nice, 95 minus 68? Is that it? That goes here?
And then whatever the rest
half of, perfect. And so if you do 95 minus 68 divided by 2, you'll get 13.5% here. 13.5%. Of course, it's the same over here. And then if you do 99.7 minus 95 divided by 2, you'll get, in this little space, you'll get 2.35%. 2.35%. And you'll have, if you subtract all that from 100% divide by 2, you'll get 0.15 for these little. And what do you think all of these add up to? Between the first 3 standard deviations, yes, but out for all of them, 100%. Yeah. Okay, so there's your normal curve. That's how they're all distributed. Let's look at some examples here. So let's say let's say you're told, the thing is, in real life, a lot of things are naturally close to a normal distribution. So for example, let's say scores on exam for a firefighter program, for entrance to the firefighter program, scores on exam for entrance to firefighter program are, you're told they're normally distributed. So the symbol for normally distributed is like a capital N, like that, normally distributed. And then the next 2 values are the mean and standard deviation, because those are the only 2 numbers you need to describe the distribution. So this is x bar, your mean, and this is your standard deviation, 20. So the exam scores are normally distributed with an average of 20 and the standard deviation of 20. So the question is, what percent of candidates scored lower than 160 points? So what percent of candidates scored lower than 160 points? Okay, so let's look at a picture of this. So we want lower than 160, and then we're going to also answer above, same question, but above 220. Let's say that's the pass rate above 220. So we'll answer those two questions. So if you look at a picture of what we're doing, so here's our normal distribution. The center is at 200. Center is at 200, and then 68% of our data is plus or minus 20 from the mean. So 1 standard deviation away. So this is 220. I'm just adding 20 to the mean and subtracting 20. So, and also 180. So the mean 200, 220, and 180 are 1 standard deviation away. And then what's the next standard deviation to the left? 200, 220, 180, what goes here? Nice, 160. And just to fill all this out, well, we probably don't need to go further there. So lower than 160 is this area right here. So I want to know what percent of candidates are less than 160. So the way you, notation-wise, you would say, you can also look at it as the percent of people is also the probability. If you randomly selected one score, what's the probability that score, X, would be less than 160? The area is, it's the same as the probability, since it all adds up to 100%. What's this probability of, so it's less than 2 standard deviations. If you compare to what we drew up there, what would this area be? Oh, is it, let's see, we're at 2 standard deviations below. So we're right here, right? So what is it? Yeah, John? Awesome. So you added 2.35 plus 0.15 and you got 2.5%, exactly. So you could put it as, you could say it as 2.5% of the values are below 160, or the probability if you randomly selected a test would be 2.5%. It's really the same thing. So let's do probability X is greater than 200 equals. So we want 220, greater than 220. So let me shade that area. Let's do a different color. Greater than 220 is going to be this part. So that's greater than 1 standard deviation above the mean. So what's that area? If we look up here. Good. We have to add all these up. 13.5 plus 2.35. 13.5 plus 2.35 plus 0.15, which equals 0.16 or 16%. Yeah. 0.16 or 16%. So about 16% of the people that are taking the exam will pass. Okay, so let me just stop for a sec to take questions.